Hello and welcome to another video where we're looking at the deflate algorithm. So I've got this kind of working. I've actually changed the code a little, so what I might do is do this to kind of walk through it maybe. So I've made some state machines because I thought, hey, that's kind of a good idea, especially if you have data that you don't have the full amount of data at the get-go, so you can kind of say, oh, I can't do anything at the moment, and then the thing that calls you can be like, alright, I'll read a bit more data and then call you again. So that's kind of how I've got it. I think that's kind of how zlib kind of acts as well, and it will be kind of important for when, for example, if we what like how I've been testing it is doing these cat tests, where what am I thinking? Like if you're piping it into the program, it can't do the seek to end to find out the file size because it's a stream in essence. It's a little chilly in here. I've just come in. Came from the other, the main house. This is like just a little tiny office. Hopefully it's not too cold for my nerves. Who knows what sets them off? But yeah, anyhow. Basically got a state machine to say like what state thing might be in. And in here we have a context and we have like a kind of reasonable size bit to save some information if need be, and I think that kind of will work potentially for every kind of way of decompressing. Perhaps with the dynamic one, this will change to be a pointer, which I guess maybe this needs to be like pointer star. That's for a later problem. Because yeah, if you're doing the dynamic, you need to kind of keep track of the state, the Huffman tree that you've kind of saved, but perhaps that can kind of get carried through. I'm not sure it can in 4 bytes, but that's what it is. I've also put this in a single header file. I think I did that before, but that's alright. So I've kind of split out some things with to let me do like append bytes, and it will ensure that there's enough space in the thing, and this ensure I can kind of also call from other things, which I do. The Huffman tree, dunno, that might need to get changed. So deflate hasn't really changed too much. The squiggles kind of show what I changed since last commit, which was roughly when I got the state machine up and running, I think. Just kind of small stuff I changed. But I believe if I like reopen this file, that will be have committed overnight because I've got a script that just does that for me. Means I need to like tidy up what I am. We're a few days off. I've got one of those like 1 a day calendars, and gosh, there is no creature better than a delicate rudeness than a cat. Which, yeah, potentially that's correct. Anyhow, and I've made like a fancy thing to do reverse bits. So this is actually like a recursive algorithm. There's ways to do it without doing like this recursive stuff. But in essence, to reverse a thing, so maybe we'll have a bit stream like this, and it'll have some stuff like that. And to reverse it, kind of what you would do is you would get the thing, you would get the length of it, I guess. That's in my window, I can't see. It's 14 characters, if you will trust me on that. So that means if we go 7 across, and we kind of get that again. Is that 7 with the 1? Yeah, and we kind of swap it around. That's all we do. And so that's kind of what these masks do. And after we swap it, we then kind of split these up into so they're like kind of 2 halves, and then you kind of recurse in and you say, well, this group of 6, and is that right? We have 3, 7. Ah, right. So we had if that is the case, we're meant to kind of keep 1 bit. No, that is 7, and that is 7. So yeah, you kind of get these 2 groups, and then you do the same thing. But if you have a bit, so say we're doing this one, if you have a bit that is an odd count, you basically don't swap the one that didn't, and so that's kind of in 2 groups, and it's got like an extra little 1 in the middle, and if we get that, and so this also has a 1 in the middle, well, not a 1, but and now you kind of want to swap these groups of things, so you'll get O1, and then you'll get that 1, and then O10 doesn't do anything, 101 doesn't do anything, that O carries in, and then you'll change this to O11, and then this should be the reverse string of this, and like I can kind of test it. So it has something different there. Oh, this 101 didn't copy right, so it should have been 2 101s, and then they kind of swap sides, and so then this would be just 101 like that, and so this should be the same string, and so we can test that by doing our reverse thing, and we can see all the bits that they kind of line up. So I kind of just made that programmatically do it for any number of bits that can fit in a 64-bit number, and it basically does it with these steps, but using masks and whatnot, and then you get the middle number out, then you make sure that you're only operating, then you take the middle out of the mask that you're kind of saying, these are the groups that I'm working on, and then here you kind of swap them, and then here you join the 2 halves together after swapping those 2 halves, and then at the end you add on any extra stuff that you might have had to take off during all these steps, and then you reverse the thing. that's how that does. And then this peak bits I have changed to be maybe a bit more efficient. I don't know. We can do our time tests in a second just to see, maybe. I think it's still a lot slower than zlib, but I'm not intending to make it fast, but I would like to make it fast enough that if I were using Git in it, it would respond reasonably choppily, and yeah, so these are kind of just help things. I've got to drop bits now. I wonder if that drop bit should be after that. And so next bytes also does a similar thing. Alright, and so here in maybe I'll go down to the bottom in zlib decompress. So that's kind of all the helper things. When you do zlib decompress, we have a context and it has all that stuff at the top, basically enough to get it going. And we check what the state is. We have a certain number of states in zlib, and if we add more to it, this number will change, and then they'll kind of tell us maybe you need to add another switch case. I think there is a compiler flag that can do that sort of thing for you, but yeah, sometimes you don't actually want to cover them all, and I've got a default in this, and sometimes the default can kind of throw that up, but that's just saying I'm not unimplemented. I think this should be this is 1, 2, 3, 4, 5, and we're thinking there are 5 things. So I think this should actually be unreachable at this stage, and maybe if it's an error, it would kind of go in there. So this would be zlib error. Just to make sure that we kind of cover all the cases, but the default is kind of if the memory has kind of been tampered with in some way in the context object, the state might not actually point to a valid state because it's just an integer, so none of the cases that we put for it will match, and it could be any number of integer. So we have this check just to make sure that we don't do it. But in essence, I thought we did some fall through things, but maybe we didn't. I think that's because we've got this dict thing, but we fall through the other ones. So the header, what we do is we, if we don't have enough bytes, we just return false, and that signifies that we don't have enough bytes, and maybe we should get some more. And this we can kind of add more to. I think the adding more to is like not as intuitive as it could be at the moment, but I could make it so. This is basically the same, check all those bytes, and then we set the state at the end, depending if we had fdict, and so far we have not, but if we did, it would actually error out here, but it also errors out here. So potentially I don't need this unimplemented, and then we can still get the warn, and we'll get an unimplemented there. This dict, I think, can potentially fall through, so maybe I'll potentially should fall through, because it is like the next obvious state. But the thing is, when you go to this might not be able to deflect, so you return false. And you might only have those 2 bits, so you do that and then you fall through, but you don't really fall through, but you come to here. And that means next time you come into this function, it'll just jump to here rather than do all the start stuff. And it does it somewhat more efficiently because of the switch, because you can kind of have it as an index into an array, which is the code where you're going to jump to. In essence, I think is roughly how switches get done. I mean, you can do it different ways, but so in here we deflate it if we kind of had an error. We might say there was an error, and if the deflate is good, then we say check the addler. At the moment we compute the addler, we don't actually check it, and then we fall through into finish. But here we potentially could fall into a different state, saying there's an error, but perhaps a different error might be nicer. So this deflate just goes through and tries to deflate blocks until it's finished, and it gets finished at some point in the deflate block, and that is because in deflate block there will be kind of a header. So maybe I'll go to the header. The header does similar things. It gets a couple of bits. If it can't, it returns false, and then that falls through. Here we just check which type it is, and then we set the state accordingly. And if we not that, go back, this is not doing what I thought it would do, and now I have no idea where I'm meant to be. It was somewhere that caught this. Literally just down there. I'll cry. And so there it will kind of set the appropriate thing. And so we'll break and we'll go through this. We've got an endless loop, and we'll find the next state. And so depending on what thing we do, we basically kind of fall out into, we're going to do a little helper method. And I actually implemented the uncompress because it is reasonably easy. So when we first get it, we make sure we clear the bits. We don't have any remaining things, so we're on a byte boundary in essence. And did that do it the right way? Yeah, so I suppose we only want to do this if context bits.index is greater than 0, then we do all of this. Otherwise, we're already on a byte boundary, so cool, fixed the bug, hadn't even seen yet. So here we then check that we have enough bytes. If we don't, then we'll clear, kind of go through until we get enough bytes. Then we get a length and an end length, and these two should be the ones complement, which is just bit twiddling all the bits. And if that is not the case, this assertion will fail. Perhaps I should get rid of all the assertions and change them to provide an error instead, but hard to know. So then what do we do? And then we kind of fall through after we save a token of data, which is the length, which is all we really need to know. And that way, if in here, when we is this right? Decompress. Oh yeah, so I figure out how many bytes there are, but if the length, which is context save, is greater than the number of bytes, then I only get that number of bytes. Otherwise, I'm only going to read the length of things in the thing, and this will read it directly from the bits data backer, which should be the input source, and then it offsets it. And if the the saved is the len, so at this point we subtract it off, and if it's 0 we're finished. Otherwise we now have a new save that next time round it will kind of do all that same check. So yeah, did the uncompressed. Don't know if anything will use it, but one more, yeah, just there. Mainly what I've been working on is the fixed compression. So fixed compression, had been doing it before. We basically do this. Now I've got like this notion of peaking bits and dropping bits, because in the state machine setup, if you say read 7 bits and it didn't match the 7 bits, you need to either unroll, so like unread, which potentially isn't possible depending on the way your backing is set up, but in this case it would be, you would just kind of add it back, but it's a little bit annoying. Instead, if you can just peak, that's fine, and then you can drop bits, which is in essence what a read would do. It would peak, then drop, then return, which if we had a look at next bits, we can see that it peak bits, it does the same equation as drop bits, so it makes me think whether this should be maybe up here, like that, and then this can yeah, and then that can just do deflect drop bits and convict and bits, and then it'll return the rec. And this, like, getting it in reverse, I wonder if it should be doing a different thing. Where uses that? Maybe I'll keep that doing what it was doing, just in case. Cool. So in here we kind of have that same kind of all text, and perhaps I can I'll do that, come here and do that. This in essence lines up with this table, I believe. So like if we have 7 bits and it's less than this number, sorry, which is the 1 7. So the bottom 4 is 7 because we got 1, 2, and 4, which makes 7, and then the top bit is 1, so we should get 1. And so this is kind of just checking everything, and importantly, if it can't read it, it bails out, and because it bails out we can do the peak at the same time. Otherwise you would have to have like varying levels of state machine, or store more stuff in the state to say I've actually read 7 bits at the moment, but I'm waiting on 1 more, which is potentially more efficient, I don't know, but well, I could work it out. golly, we went somewhere different. I want to now check what happens after that. So after we get that, we're now checking against this blurb of text where if it's below 256, it's just a normal byte, and if it's 256, then it's end of block, that bit there. And then the rest is, if it's over 285, then it's an error, otherwise it is, that comment can kind of go. It's obvious what is happening, I think. I mean, it can maybe have a space, because things had a space like that. I don't know. Right, so after we get the code, we're now looking, so now we're kind of looking for the length from that code. So it's not just a byte, we're looking for a length out of a length distance pair, which is this here. And this is kind of from 3 to 258. So it can fit in a byte offset by 3, but because I've got 32 bits to play with, and this distance is going to fit in a 16-bit, we can save the code and the distance together reasonably easy, even if it's 16-bit for this code here, which will be like 9-bit, just so it can get the high end. But anyhow, what we do here is we now do basically the same things. If it is one of these start ones, so annoyingly the table's set out like that, but if it's this first table where there's 0 extra bits, then we have a different state for that. Otherwise, the bulk of the case, we have extra bits, and I think 285 was another one. And 285 has a length of 258. It's great for dyslexics, so I put a little comment in there just so you can kind of be like, wait, is this wrong? But no, it is actually right. Otherwise, we kind of fall through and read these extra bits. So here I've got a little helper function to do so, just because it's got a few like edge cases. It can probably, because of the way it's kind of set up, I could work out what the offsets are. Like there are 4 things for every number, every number of bits. So based on that, I could work out, well, if we start from the 265 and 11, I can work out what the code is. But I think for readability, it looks a bit nicer like this. And I've got these comments that, does this need to be in the reverse order, because I can't actually recall if it's right. But my thought process is, if I can get it working with a bunch of various different test cases and perhaps encode more stuff of my own and just try things out, do that. So in a sense, this kind of returns the length, so the third column in this kind of thing. And from the length, we save it, we basically just save the length. We don't need the code anymore. We've finished with the code. We have the length out of, golly, that wasn't what I wanted to do. Just reloading all those pages just because of the scroll. So we've got the length part of this length backwards distance pair, because we know it's not a literal byte, and it's not the stop byte. So we got a length. Now we need the distance. So for the distance, there's another table that we kind of need to do. And so here we kind of get 5 bits, so it's always 5 bits, I think, is what I take it. So it only lies between that range there. We can kind of assert that. And in this we have some extra bits. So if it's less than 4, it's this. And this table here we can potentially also work out a bit more efficiently, but I do not, and I kind of spell it out. Yeah, I spelled it out, and I was like, kind of just gave up halfway. So that's kind of, in essence, all it is. And assuming that fix is working, then we get to compress fix copy, and then we have saved the length up 16 and the distance, which is a 16-bit. Which I've said 32-bit there, but it doesn't need to be that. I think I made it 32 just so like the EOF kind of makes sense. Otherwise, like you could have, no, I think I don't need to think about that, because that number is like half of the UN. In essence, the negative 1 will be all ones. I think in essence that's kind of how it ends up. And so if we look at the hex of 32768, we can see that it fits quite snugly in 4 nibbles, which means it's 2 bytes, which means it's 16 bits. So it fits quite snugly in that. It does have the top bit set, so this could be perceived as a negative number if it were an int 16. But like, I don't know. So the man page of this is, it just represents a negative value of type int. So maybe I do want it to be 32-bit, and here we can just do uint16t, make sure that we're only kind of doing that. Otherwise, like, it shouldn't really, actually. We've already made the assertion that it is small, and we're testing unsigned, so that should be fine. And we already checked for the EOF. So what happens in the copy is we get the length and the dist, and we check that the distance doesn't go back too far, which I think somewhere in here it kind of says that. So it can pass like block boundaries, so we have to kind of keep the same thing, which I believe in our thing it does that. Distance cannot refer past the beginning of the output stream, so that's why I do this little check here. If it is more than the current size, then we would be reading negative. So then we kind of just get the bytes from where we currently are, which is data plus size, and then we subtract off dist, which should be legit. And we do this while length is greater than dist. And the reason for that is, say this case here, we have an x and a y, and the length is 5, so it's more than distance. If we go back 2 and just copy 2, which is all we can because we don't know what happens next, we get x by x, y. And at this point, we have length of 1 because we need one more to go back. But we can actually go back 4. So if we had like a length of 50, we now are copying 4 bytes at once. And so in essence, you would copy doubles each time. And then we just add on any extras, which maybe I'll wrap this in a, if len is greater than 0, do that. And at this point here, we have copied all the bytes. So we don't actually need to read anything in this state. So we then just kind of go back to the fixed state. We could save our saved data, but I think we don't need to in this. Like, we are not using that, and we're like saving it. Cool. So that's that, and it kind of works, but it also kind of doesn't. So if we do these tests, it's probably gonna take a bit of time. There's a chance that I will either pass or fail, and it really just depends on the test case, which does not make me happy. I kind of want it to run all the test cases so I can see what's failing. This is one that fails. So what we can do is I output the hex as you kind of notice, and here we can get that, and so like now that's proper hex. So this is the hex of coming in. So if we get the last one, so this one used to fail, it now succeeds. So it was because I hadn't implemented this reverse thing at all. But now, and I think at this point here, after it does the S, it then goes back and copies space and yikes again and gets to there. But now we're kind of failing on a second one. And I mean, that doesn't look that right. And we can also look at examples. Yeah, is this what I want? And if we look at what this says, yeah, so this is what this should end up with. Maybe I'll do that. And compared with mine, we after this D, we're meant to be saying donkey, but we get a bunch of D's instead. So that's kind of fun. How do we go about testing this? So my program, in essence, just kind of takes stuff from input and decodes it. So what I can do is, I think I even have a GDB. We had a break at various endpoints. I think I might want to do a break on maybe on here. So this was source/zlib.h, and I wonder if the font is actually big enough. And this is 443. Maybe I'll do it there. Just so we kind of get a couple of things. Right, so here we can see kind of where it is up to. So at this point here, we can kind of have a little look-see and see what our context has. That's kind of weird. Like the bits doesn't it seems like it's kind of maybe I started it at the wrong font. Apologies, we'll just have to go a little. Well, I can go like this and maybe like this and like that. Nah, because now I need maybe like that sort of size. But now it I don't know. It is just what it is. I can do that sort of thing, and yeah, that's probably good. So here we can see what things are looking at, and so here is the data that we were kind of reading from. A current index there. We've got 24 valid bytes left in this, and decompressed, we have decompressed a bit. So we've decompressed blob 39, I think a bit more than blob 39. If we did something like x/27, and we do C, and if we do this at context slash decompressed data, that will show us all the characters and the things as we go, and we see that there was a null byte, so we get this blob 39, and then this kind of thing here. This is actually kind of but that plus what are we? 1, 2, 3, 4, 5, 6, 7. Oh, can we do this? SDR plus SDR len of context slash decompressed dot data. Bit cursed, but say it has a size T, and then like add one more. Yeah, so that like kind of gets past the null byte. So this is currently what we're looking at, but we don't have too much to say. So I wonder if instead of doing that we do context slash decompressed dot size. So this is pointing at the 276, but which one is it? If we do -1, we can see we get the S from the yike. So we are kind of pointing at just here where it starts getting to gobbledygook. So what do we want to do? I kind of want to see what this is meant to do. And so what did I have? Source third party zlib examples and a.out and decrypt that. And have but if we are cool. This seems like we're running from the wrong one. Layout source. So if we continue here, and now if we look at context, and it doesn't like remember. I wonder if I can kind of set that up. So I want to look at context decompressed dot data plus SDR SDR len of context decompressed dot data plus 1. I want to look at that. So we have vanilla, and I assume that we're kind of pointing at that point, and we can confirm that by looking at decompressed dot size and minus 2, say, and we get the A space. So yeah, we are literally at the end of that vanilla. And what we're wanting to get out of this is vanilla. So ours was failing on that failed 2 and A dot out, and what would that kind of say? Ours was failing on the D, so I kind of want to get past this. So perhaps if I go continue from there and have a look where we are. So this is the length of our string, and if we did this, so we are at the end of that. So at this point here, we want, I suppose we're getting the monkey, but we've already done the D. So I would imagine that we want to go back. So we want a length of 1, 2, 3, 4, 5, 6, I assume, because we'll get up to there. And they'll give us a donkey in a space. So a thing of 6, and then distance will be 1, 2, 3, 4, 5, 6, 7. Is that kind of what I'm thinking? This is tiny for you now, sorry, but what that kind of means is we want a code of 260. I think, or 261 now, but we can step through and kind of see what we get. But we already have a code, that's right. So if we look at this, our code was saved. In fact, we can look at what it is. It's a 104. So that's a 260. Gosh, it's just what I thought it would be. So that means it's less than this, so we should get a new saved value. So if we look at this, our saved value is now 6, which is what I thought it should be, a length of 6. And now we want to get the distance, which means we'll kind of go through again. We'll get the length. So we get a length of 6, that's still good. So the next code, so we get 5 bits, and it says distance codes 0 to 31 are represented by a fixed length 5-bit codes with possible additional bits in the table above. So we want this, and what was the distance I was thinking it was going to be? It was like, well, if we've got a length of 6, we need to go back 7, right, because we're not including the D's. So if we want 7, we want a code of 5, I would say. So if we get this, I didn't want to do that. So we get a value of 1. See, that doesn't seem right. I feel like an assert should fail at this point, because we should have a valid distance. So where is this? 473. So at this point here, we should have code is greater than 0 and code is less than 30, because we should Distance code 0 to 31. So the code can be 0. Code is 0, and that just makes a distance of 1. So no, don't do that. But a code of 0 does not seem right, because now if we look at context, our saved is golly. Well, if we look at saved as hex, we can see it's 6 for the length and then 1 for the distance. So that is wrong, because our bits, what does our bits say? We have gotten the bits, so I think I want to get here again. So we can run this by doing fail2.x, do something like that, and yeah, do this again, please. This sort of thing, but we maybe search for the strlen. Yeah, so we have the vanilla. I don't want that one. Now we are up to the D. So at this point here, did we got the code? So at this point here we fixed a length. So before here we should have got the code by doing this. So I feel like that did the right thing. If we get the right thing, we drop some bits. If we peak, if we get the right thing, we drop 8 bits. Otherwise we peak and then we drop 9 bits. I wonder if that was a little bug. Like I do wonder if that was it, because that is 9 bits and we would have only dropped 8 bits, so there would be 1 bit still kind of sitting in the stream. So I think if I do my thing again, it still doesn't give us the right thing. XD, yeah, get this again. We get a sig fault, alright. Fail to, yeah, run this, layout source, I'll just check a thing. That can be a question for later. Right, so if we continue from here, likely continue from here. We haven't got our thing, but if we ps and context / decompressed data plus int of strlen of context decompressed data plus 1. Alright, so I don't want that one. Do want this one. So we get the code, and our code is 260, which should make our length 6. Perfect. Now our next code is 0. It's still getting 0. Perhaps I need all my kind of infoing info. I think I want if. Well, actually, it seemed like it had that. And define info, and this can just be, needs to be a valid thing, that we can have it as something like that. And so now we always get the info. So I think if we do this, I don't really want that one. Maybe that one and these ones, these ones, these ones. Maybe even these. Cool. So if I did all of that and it kind of run my one, I don't like things. Maybe if I do a make command, we get, we did info, cool. Maybe I did want that info for that, and here I probably want to do like a hex or something of these bytes. So I already have kind of a hex dump in source main. I don't call it a hex dump, I call it this thing here. So maybe I can make this little hex dump. So we can do hex dump of uint xt data and size t len, and if we did that, we could then just do a hex dump here of file data and size, and that would probably do the trick. And this whole thing would get to here, and so if we replace everything in there with file data with just data, and maybe ask me, we had a couple, and if we now replace size with len, and maybe do that, and don't do this first one, no, undo, I see, we've got that first one, so don't do those two, do that, and that's the only one we did. So this can be kind of yanked into source zlib maybe. And so I guess this just needs to come here and we can make this a thing. It's not really a thing, hex dump. It's not really like that related to the living. And then where was I that I kind of wanted to do this thing? Get me to I would have thought this would have, I don't know where I was searching before. Is this where I wanted to be? It was in the append, but not the append, the append bytes. So I think here I want to go info appending bytes, and then do a hex dump of source and len. Do something like that, and then we hopefully see like some things. Like when did I want it to tell me? So like after monkey, I guess I want it to maybe do it here. Exxd minus r failed 2 dot hex. Yes, do that and continue. Exxd minus r failed 2 dot hex. I would have thought. Would have worked. Finished, but like it didn't break at the point that I wanted it to. So at 443, we didn't really want it to be there anymore. Is that because we like changed things? We wanted it to be here, didn't we? Break the source, break even source zlib.h and 478 And if we run that again, yes, and then continue. Maybe I want to like say just something here, info, fixed length here, and I know that it is the second time that hits that I care about that. So not that time. This one here. I just had zeros. Oh goodness. Why is there no bytes there? So context bits. What does this look like? Data plus 23. And like, can we x all of this? Have we just run out of data? No, the size is 23, so the data should be still pointing at a valid thing. So it should be looking at like it should be getting 5 bits from this. But we had golly, is that like, no, that's just the address of it. The index was that, isn't really, index is 7, which means that we've already got 7 things from here. So we'll get the next bit. Maybe if I kind of look at things like this. And like maybe also is that as well. And so we should, I don't know why this is getting the wrong number. I want to step into this. Step into this. Right, so we get like kind of 2 things. So what do we get from red bits? First, I guess, what is bytes? We reckon we only need 1 byte for 5 bits. is like 1. So we'd get 5 plus 1 plus 7. And how does it kind of go about doing things? Alright, so say this one is that, and if we shift it left 7, we get just 0. But if we get the 1 as well, then we should get a 1, which is not what I wanted. But if we get this number, and if we get that whole thing, oh, apologies, if we get that whole number and shift it right by 7, then just get the bottom 5 bits, we should be getting a different number. So I think it's this kind of calculation here that is not kind of working. So it was after we did this, we went in here, so we get some bits, we peek at some bits, we peek at the bits in reverse. So I guess how many bits we have in the current byte would be it would be 8 minus the index. That's how many bits we have in the current byte. And how many bits we need is more than that. Perhaps I need to kind of revisit this. We can start with we need 0 bytes to start with, and then while I kind of want a one-liner. So this is how many bits we have to start with, and so if we get this and subtract off the bits we need, which is like 5, what would we get then? So this would be 8 minus 7, so that would be 1 minus 5. So that would be like -4. Which kind of means I need 8 because we have at least 1 byte, or maybe 7 plus, like minus that thing. Which would give us 11, which if we had 2 bytes we would have 16 minus 7, which would be 11. So yeah, I think it is that. So that was 7 which I think is just a magic value to make it friendly. So we can work things out. So this minus bits was what we kind of wanted. So we could perhaps make things a little better. So this would be 7 plus bits minus 8 plus context bits dot index. Now, is that right? So there will be bits plus context bits dot index minus 1. So that would be 5 plus 7 minus 1 in this case. Now, and is that right? That's, yeah, that is still the same. So, say we had an index of just 1, so we actually have 7 bits left on this, so we can have 8 minus 1, so that's going to be our 7, and say we wanted, so we got 7 bits, say we wanted only 5, so we shouldn't need to pull in any extra bytes, we should be able to just treat this one as is. Now if we had that, that would be 3, and then 7 minus 3 is, so this would be 11, and you would divide it by 8, to get 1. What was it, 7 minus 5? So, yeah, say we had index 2 and bits 10, say we want a 10 digit 1. So, in this case, what would we have? We would have 7 plus bits minus 8, well, no, it's actually bits plus IDX minus 1, so this would be 10 minus 2 minus 1, so this would be 7. So this doesn't quite seem right, because in this case we should want 2 things, so we should be going up somewhere, and I wonder if this 7 was a magical thing, where this was actually IDX, and so this would be like IDX minus bits, well, minus 8 plus IDX, and then we get plus bits. In fact, was I? No, I did kind of pull that over. Right, and so this would be 2 times IDX plus bits minus 8. I don't know if that seems right. So before we had IDX of 7, so this would be 14 plus 5 minus 8. It just seems too high, so there'll be 19. So there'll be 11. It's the same. And then here we would have, so this would be 4 plus, well, I guess it was going to be the same because the 7 was always the same. But here we have 4 plus 10 minus 8. See, I feel like we need to, I want to see how many bytes we need. Based on things. So I guess how many bytes we need is just how many bits we need offset by the index. Maybe that is what I want. So here we have kind of 6 bits available, so that's the 8 minus IDX, but we need 10 bytes. So I guess that's like this sort of thing, and there'll be how many like extra things that we, or is it just this plus the number of things? So yeah, because what I want to do is find out how many bytes I need to kind of treat the data as. So what this is doing is this is just a single 8-bit number, and we offset it by index. So we're kind of shifting it down by index. I mean, we can always like just do a cheeky +1. I know this is wrong. I feel like it might just be something like bits plus index, and it would overshoot. Well, it potentially will overshoot. And then +7 divided by 8. The +7 divided by 8 is to make it, so say we, say we had index of 2, IDX 2, and length of 10, say. So what this was going to have was just that. Yeah, maybe I wanted this. But yeah, so here we would have 12 plus 7. So we would kind of have 6 bits free, need another byte. So here we would get 12 plus 7 is, gosh, 19, and divide by 8, that goes what, twice into 16, so divided by 8 would be 2. Now say we had index of 0 and len of 8, so that's like an edge case. We have 8 bits free, no need for more. So we should get 1 out of this. So we should get 8 plus 0 plus 8 divided by 8, plus 7 even, divided by 8, and it still equals just 1. The plus 7 is so you go almost up to the next number. Say if we had IDX 0 and len of 1, we don't need any more. But if we just did 0 plus 1 divided by 8, that would be 0. But if we add on the 7, then we would get the 1 byte. Cool. So yeah, I think it's just meant to be that. Now, was there another place I was doing that? So bytes equals this one, just these 2 places, and that's just how many things I'm reading. And so here I probably have a bunch of junk to clean up, and here, I don't know, like, let's quit that and see what happens. That looks like it might be getting the right trick, and maybe I'll go to this info and we can just do info false, and if we redo, it didn't like that for some reason. It's because we're like unusing all the variables. How do we get around that? Because, yeah, I don't know. How do you go through each of the variadics in a thing like this? I kind of just want to, like, dev null. Perhaps I need to kind of make that. So like you do stuff with VARs. Is this how you do it? VAR? Yeah, so we have a function. How do we call you? So we just do the dot dot dot. Easy, and here we can just like wrap the format. Is that all we kind of need? I don't know, like, because it's not really in the I think this still won't kind of work. Like the hdist is only used in there. Though to be fair, this potentially isn't working. I would be happy just kind of doing that, because like it's a sign that the hdist probably should be used elsewhere. Cool, so we're still doing a hex dump somewhere. I should like make a patch for that plugin to do that. Did we still do hex dumps? I don't know why we're... What's printing out all the things? If print f, and we do it in the hex dump, and print bits. Yeah, so the print bits, I think, how do I want to go about this? I think I want to do, how do we, I kind of want to match everything with print bits. yeah, so we do stuff like this, and then we can like yeah, this is what I want to do. But here I want to. I kind of want to do this. Nah, so. I think I just need to not be fancy with my infos. Take out that. And I think I don't really want to do this, and we can just have that, just so I can do things, and here we can do another kind of comment out. Right, so we still do some infos in some other places. That one we can do that. Is that what we want to do? Yeah, cool. So now maybe do another test and see if that kind of works. I mean, the test might work, but it also might fail. This one fails because, yeah, this one was interesting. I saw it fail another time, but so if we do fail 2, fail 3.hex, we've now got a few. That wasn't what I wanted, but and set this to be fail 3, and if we run that again, right, so we have like not got all the data out of that, so fail 3, and if we get the example 1, and fail 3, so this is the bottom one is what they had, and you can see there is a Y on the end, and here we've got like an extra space, so I think this is where perhaps my distance is not right, because we're probably at this point and I'm copying that space here, or yeah, for some reason I'm getting an extra space, and it'll be doing kind of wraparounds. So I think this one here, so the GDB, and we can do that, and I think I kind of want this to be in fixed compression code, compression length, so we can probably just break that, deflate fixed compression, because I know that it's kind of so maybe I'll do a display on as a string of context decompressed data plus int of str_len of context decompressed data plus 1. So it won't have anything now. Is that because like it? The context. Yeah. So I think for now it's I want to like break break zlib.h 469. So no, just continue actually. And dr2. And so now if we continue, so now if I did that display of string, I feel like it is alright. So now we are seeing the Scooby. So what was mine planning on? Scooby looked right, so I reckon I'll continue here. And now we've got the monkey Dumpty and so here I think we're doing something a little odd. So we got the code 260. So 260 would give us 6. So going back 6 from gosh, where is it? So 1, 2, 3, 4, 5, 6. So I think it should be at the U. Does this actually give me 6? It does give me 6. And here what the code is just 5, and so 5 in this one would be an extra bit, which would be 7 or 8. So here we have the len and the code, so those were the two things that we thought. So code is less than 5, so we should just get 1 bit more. We get 0, so that should give us 7 as our return value, so 7 was the correct thing. So what does p context decompressed? I really wish data plus I want context decompressed dot size, and I want to go back distance. So we're looking at the umpty. That does look right, and the len also kind of seems right. So 1, 2, 3, 4, 5, 6. So it would get like an extra space. So I feel like the space is happening at the end. So we should get that Humpty with a space, and we're back to just fix things. So now what do we get with the code? And did that do a peak maybe? Want to make sure that whenever you peak, you drop, if you want to drop. So I think it was happening in all of those cases. Here we peak, that's alright. And next bits was doing it. Right, so we're not actually doing it. And here we're just getting the next bits. And then this code, the code after is a 260, which should be another back thing. So 260 of length something, length 6. So we can kind of step through, and we should get a length of 6. Yeah, cool. And then this code is 7. So 7, we need 2 bits, and this is potentially where we're going wrong. So here we need an extra thing. So 7, we get 2 bits, and I wonder if it's meant to be in reverse. So here, if we just fin that. So here we have a value of 10, which is like reasonably high, I guess. So we have the code, which is like 111 at the moment, and we're going to kind of add that 10 to it. And I wonder if it's meant to be 11101. And here this little magic is meant to be doing, so we're starting at 6. Well, the range that we're mapping onto starts at 9, and we're going to map on code, but our code is offset by the start of the other side, which is 6-2, because we've shifted up our code. So that whole thing should get us 15. Does that make sense? No, that doesn't make sense. Because the range can only get up to 12. So code is that, and what is code? Wow, what's 6-2? So that's 24. So we should get 6-2. We should get a difference of 6. I feel like we just need to ignore the. Yeah, we just need to ignore the bits that we are currently on, which probably means that there's another extra one that we do. So length extra and dist extra both probably need to get done. Or is dist extra the one that we just get it. So we're wanting to map onto a range. So it's going to start at 9, and the distance up that range is just going to be like our kind of number. So then next we had next. So that would be just 9 plus 2 would give us 11. And if we had 3, which would be the max number of digits, then that would be that. So I think that's actually kind of what I want, and do stuff like that. And we don't need to really worry about any shifts and whatnot. Which one was that? 19 plus next. So this is the other table up here that we have here. We're mapping 19 with a 2-digit thing. So here we have 35. 67. That makes things a little easier to kind of copy paste as well. So here we can probably fill out these. So maybe we can bring this back a little bigger. So this bottom table here is what we're kind of looking at here. So 10 is we've got less than 10, we've got 3 bits, and we start at we're still in resize mode, and we start at 17, and did that not do what I wanted? And here we add on another bit, and the 17 changes into a 33. And here the 33 changes into a 65. May as well just finish off that wasn't what I wanted. The 65 goes into a 129. Because this needs doing. It is kind of grunt work, but sometimes I find it goes better when I'm doing it on stream. So less than 20, that will be 513. And the 513 is now 1025. The numbers are getting bigger. 2049. And the 11 bit is 4097. 4097. And this changes to a 8193. goes to a 16385. 16385, and I think we can have the unreachable at the end there. So perhaps that is kind of all that's needed to make this kind of work. So fail 2 works, fail 3 doesn't quite look like it's working. In fact, has it gotten worse? Because we did a doobie scooby, and then we get like an extra CASC there. That's kind of interesting. Like, why does that happen? And I wonder if the stuff that I just did kind of made that change. So length extra. If we have more than 265 because we have extra bits, and if we're less than 269, then we want to get 1 bit. So we want to get 1 bit plus. So it's going to be the 11. But we need to get the difference between these numbers, because we start at 11, but we actually go all the way up to 18. So we don't just get next, because next only gets us one bit of information, and we need a few bits to get up to there. Right, so how do I want to kind of map that? There's two things in each one, so we could do this as code minus 265. They'll get us the difference between that, and then if we multiply that by 2 and then add on the next, maybe that's what we need to do, and unfortunately we need to do that with all the others, so this would be 269 times 2 plus that. And the times 2, I wonder if it's just shifted by 2, because like here where we have 2 digits, we've got 4 options, so we go up by 4 each time. So it'll be that difference by 4. Which, the first one by 2 is just that, and then that's by 2. So I think I can really replace this by 2, and it's like maybe do like a UNT offset equals 1, and here the offset is going to be that, and here offset is going to be that. UNH T offset equals 3 this time, then this will be offset, and here the code will be code minus 273. And then shift by offset. Yep. And here we have offset and unit ht offset equals. Didn't think that was the last thing I did, but that's alright. I did like backspace, which isn't quite the same. Code minus 277 by the offset. And like there's a pattern here. There is definitely a pattern. Like the base number could probably get changed, and this is 281 offset and plus the next. So it's kind of similar to what I had, I guess. We pasted the wrong one at some point. Kind of makes sense. Yeah, I kind of stopped doing. Gosh, got up to 13. Probably should have done a macro for this. Right, so. Now we get here, what I can do is, golly, maybe like in all of here we can we do context slash dot start that, and just replace that with context slash offset. EZ, and then all these numbers I kind of want to make so I'll do the first one manually. So this is this table here, so this is plus code we had code minus like offset, which was the 281 up there, so that would be the 281, so that's like the start of that, but on this side, so this is the 265, but not 265, 4, and we are shifting by the offset. Right. Now, what the trick is, is here we want to do code minus 6. Luckily, 6 is already kind of here. So if we go like 4 up and then 4 up again, and then here, maybe like find that, and then go over and then yank to the end, then 5 down and 4 down, and maybe go here and do this, and then we can do something like code, I'm recording something cool, and then we can do minus and then paste whatever we had, and then shift by offset, and then we can go 5 down to the next line, and we were like roughly there. And so now if I do Q, it should grab the 8, I would say. Code minus 8, perfect. And now it should get 10, 10, and now it should get 12, now it should get 14, now it should get 16, now it should get 18, now it should get 20, now it should get 22, 24, and 26, and if we do it one more time we get 28, which is that one, which is this case here where we start off the 13-bit things and the offset is 13. So the offsets all kind of go up as 1, and then the offsets all kind of go up by 1. There's better ways to do that. Right, so now what does this do? Oh, it doesn't like something. Right, so maybe if we do this, so it wants parentheses around that. So maybe I want to do something like, because I've got this in a few places, I want something like code minus, and it's a 0 to 9 star, and then we have another thing. And then we have offset, and I just want to replace that with bracket and then that, and I think that will do what it kind of wanted me to do, and it did it 18 times and saved me doing it 18 times. Looks like it's just got the same thing. We're getting like weird extra space. Did not change anything. And if we did it with the third one, yeah, not that one, failed 3 things. Humpty Dumpty, so we just get that extra space from somewhere. So yeah, I think I want to do this GDB fixed compression, but I don't want to stop there. I want to fixed compression. I kind of want the in fixed compression. I want it so only if it's in here, like 524. Let's say zlib.h 524, and that worked. And if we continue from here, we should get to a point where we can see what the context is. Perhaps we can see what our string looks like currently. So we can look at context decompressed data plus int of str len of context decompressed data, and then plus 1 on the end of that. So at this point here, I think it was doing fine, so it should get the Scooby fine. So I might just continue. And it was this point here that it was kind of failing. So layout source, and if we kind of step through things, we can see kind of what happens. So here we should get a len and so length of 6 and distance of 7. So if we get this thing in context decompressed.data dot size, and then -7, which is the distance. So that's what we're wanting to copy, but only 6 things of it. That's my understanding. And so we should get empty with a space, notably with a space. So I guess we do the copy and we get Humpty with a space, and so we get Dumpty Humpty, and it's called the space. And so now we get a code. So what's our code now? It's 260, which is another kind of backlink. So now we're getting 6. It does like a bunch of things. So we should get a length of 6, and I think I don't want to do undisplay of 2, because that was just that, but we could do it of dist. That's alright, you'll pick it up when you can. So we should get a dist. So what is our dist? 15. So it is copying a space. I'm telling you. It reckons it should. So just of 15 should be 267 and that. So like the code would have been code would have been 7, so 7, and our distance was 15, so that should have been kind of in the middle of that. I wonder if it's because of the reverse bits. So there was like a fix me, that's later. So we'll see which case this is going to go in. Well, actually, no, we kind of know. So it was in the code of 7, so it was in the 2-bit case. So if we did something like here in rev, and if we run this again now with fail3.hex, and yeah, run that bad boy again. Recompile, that's alright. That's probably because it doesn't really. Well, I might not have done the minus R, to be honest. Cool. So if we continue on here, if we can we get that display going actually? So we can continue from here, and at this point here, we should get a different distance, and so we should get the empty at this point. Yeah, so we empty with a space, and so we get a code 270, so that's the length of 6 again, and here we get a code, so the code is 7, which looks about right compared to the table. So because it is 7, we need to do a thing. I think this is going to go into the. Oh, it hasn't gone into the next bit's rev. Frame 1 thing. So this is that wasn't the right one to do. It was this one. So I'm wondering if we run that. That looks good. That looks good, right? So we can just quit that, and if we run that, that's the output that is meant to be, and this is the output that I have. And so we could do some MD5 sums, and we could see that they are looking roughly the same. So yeah, maybe I'll do a test and see if more stuff kind of fails. Well, in fact, more stuff will fail because stuff will go through those cases that don't do. So perhaps I can. This one was a different one actually. So this, what do we want to do? So fail4.hex, I guess, and we can put that there and bring that there. And if we do. Don't care about MD5 sums, just care about what it looks like. So that's me, doesn't look right, I guess. And minus D, this one, and do that 4. So it does, after the doobie, at this D, it gets the wrong thing. So the distance is going back further than it should, right? Potentially a bit's width. So my hypothesis is that if we kind of go here and do this and maybe search for that and do it a few times, and like I wonder if it's meant to be done here, but potentially it's not in this compression length extra, but surely it would be. So that's what the example does, and this is what mine does. It was a little slower. Oh, rebuilding. That's why I had to kind of rebuild the sources. Right, so that looks like that is working now. But I'm wondering if that length one works, because we're kind of always getting length in this stage where that did. So we passed, but if we run it again, we might fail. Is this like running all of them? Nah, so this is just like running one, and so that's the doo-doo donkey one. This is the Scooby Humpty one. And this is saying, yeah, size from end. That's right, that was like failing an assertion at one point. But I think that's because that Doobie Humpty. So I wonder if I can say which ones I want. Because I feel like it isn't quite working completely. So some things we can do. If we look at my one, this is some data. I want to kind of generate a bunch of data with maybe a long length. So like maybe if we do something like printf, maybe even if we start here, we can do Python -c, and now we can print a times, I don't know, like 100 plus bcd plus a times, and like what's a good length? So 194, it will have some kind of copy over. So if we did this, we can't do that because Python needs a string, and if we do Alt Alt B, Control B, that's the one. That wasn't what I wanted. That was also not what I wanted. So I want that, and that will kind of print us a string with some stuff in the middle. So it will kind of get compiled a little interestingly. So if we go source the third-party zlib examples and a.out, and I think that has now just generated some stuff, and we should get the same information back out, I guess. I mean, that looks like it's kind of just doing the trick. So zlib data, non-zlib data. So I guess the length is correct. So I wanted, I did 194. What if I did, like 200 is square in the thing, and it looks like it kind of does the trick. I kind of want the original data. This of diff temp. I have that. Hey, we do have a difference somewhere. Can we see where? I think we do somewhat have a difference. So I think a better way to do this is to maybe like add on an extra string at the end, so we can see that it has kind of cut that off. And if we go source third party zlib examples a dot minus d on this, it will kind of include that. So it's done some different things, and I wonder potentially I should I don't know, kind of yes, do that. Yeah. I kind of just want to make a commit out of this. Kind of working. And that way I can do the thing that I thought that it might need to be. So this one has some things. Maybe I want to start here, and we can actually this first one, it doesn't need it, but it probably should out of consistency. So start here, down there, find that, and then do that, and then down 3, and then Q. And so now if we do Q, 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 E, Z, and I wonder if we do this again now, it looks like it has kind of done the right thing. So maybe we can MD5 some whatever came out of it. And when we did this, we can just MD5 sum it. It's a different value. And like that's the right value. Right. So I wonder if that little test I did also broke some other things as well. Who knows? I literally changed the way the link's kind of working. I kind of want that, and do that. That looks like it's kind of working. Cool. So that's all working, but this thing did not work. Maybe I want that out to a temp, and like this to XXD, and that can just be a diff of that with temp. So we only, this is the real one, this is not the real one. That doesn't make sense. Oh, goodness. We got the BCD. Surely that's not right. Perfect, cool. So now if we do an MD5 sum of this, it's the EB something. If we did one with this, it's the EB thing, and if we did just this, but we add on the BCD, then it's the EB. Perfect. So does this all work with all the things? Gosh, I thought I'd broken it, but I hadn't. So I think, what else could I test? There's various things you could test, but I think this is somewhat a reasonable zlib thing. Gosh, nearly 1,000 lines. The spec I would not say is the nicest to read. I haven't even done the reading in the dynamic Huffmans. I also haven't done the zlib. Yeah, compression. We don't compress. So the zlib, the adler, I should probably do a little check. So when we are in the adler, what do we want to do? We kind of want to get 2 bytes, I guess. We actually want to get like quite a few bytes. Like 4. Just 4, thanks. And this was a uint 32 T. And this is the adler, and it should just be the same, I think. Adler equals, it should be the same as S2 times 65536 plus S1. I believe that is what my thinking is. Right, we're not allowed to do this because we're comparing uint 32 and int. Does this change it to an int? Because all of these are uints, uint 16s. So I guess what I kind of want to do is uint 32t of s. Easy. That would have been nice. So do we clear the bits? Is that what we're... like I kind of don't know if we're meant to clear the bits or not. But maybe I'll do a GDB bit break on line 806. That seems good. And if we just continue from there. Now we are at the point where make a little bit of space. So we have S1 and S2, and we should have some bytes in this string. So if we look at context bits, is that deflate dot bits. Right, so this is what we have. We've already read 2 bits off it. So I think I want to do a p-t of bits.data, and maybe of the first one. We've already read 2 things off it, so it would be something like that, up by 8, and then pouring on the deflate. Deflate.bits.data of the one that we currently have. So I think this is kind of what it would do, but it would shift off by 2. So that's what the current bit stream would be. But if we clear the bits, then that kind of would look more like this. But it's still kind of just nothing. So p context deflate.bits, and we have 9 things. But we want to read like 8 bytes. So can I just do something like this? call it a uint2t, and just like dereference that bad boy. So that's what it would be. So those are the 100 at the start. But I think if we kind of offset it by 1, it would not like that. I think just that. If we do that, that's kind of what it should look like, right? I don't think that's right, because S2 looks like that, and if we times 65536, we should get basically shifted up, and if we add on S1, that's what we should get. But what we have in the stream is that, or that. Of the uncompressed data, excluding data computed. And we've done it on the decompressed and only the amount of stuff that we had, and we did this, and both modulo that, so it's S1 plus the data modulo that, S2 plus S1 modulo that, so we should get that, and then we start at 1 and 0. It's up there. So we kind of need to like get rid of the byte. Compressed data is kind of all done there. We have clearly got the stop bit, and like we like it's not called stop, is it? Of course it is not. We get like a 256 at some point, and then it becomes finished. And this is after we have gotten the code. So the code exists and has been consumed. That's kind of my thinking of it. Yeah, just want to check a thing. I've got some things I need to do. That's all right. And what was it that I wanted to check? This thing here. Yeah, got a bit of time. Right, so we get that last code and it is a thing. And it's stored in like that order, because like what I'm saying is like the data is kind of there. If we shift that by 3 Is that what we... Yeah, so we want an FO, we want a 1-1. Yeah, so if we clear the byte that we are on, and then we have this weird thing, and then we have it in the network order, and so we get A1, 1 4. A1 4, yeah, A1 4, then 1-1, then FO, but it's got this kind of odd thing first. I wonder if that kind of always shows up. And it seems very, I don't know, precise. So it's just all stored in the compressed data, which is this format, and we're basically reading block header, so we did that. It wasn't that, so it wasn't that, and then we looped until we got end of block. So we break from this loop, and then we loop until it's the last block, which the last block was set by B final. Which gets set to context last. So where does the last kind of get checked? The last does not get checked. That's kind of interesting. So we deflate a block. When we get to deflate finished. Deflate finished, how did we get to this state? We do get to this state, but I guess if deflate is finished, we should check whether it's the last block. So the last was on the deflate context, so I think this should be while not last. And I have a feeling that if context slash state equals deflate finished and not context last, maybe I just want to do that here without the and. So if we're here, we kind of just want to restart the machine. Deflate header, is that golly, header. So I think that's kind of what I want to do, and then we'll kind of go through and get another block. And so this next block, we would get 2 bits. I kind of want to see what happens here. Maybe we can do a break in deflate header and like run this again. Maybe I'll just start this again with this, and we can break with deflate header. So if we run this now, we redo it. So we're in deflate header. So if we look at our context, the star context, that's what I want. If we look at our context, we haven't actually done anything. So this is like the legit header. And if we go there again, we can now see that we've got 48 bytes, and we can see that's like 40 minus like a bunch of stuff. And we can even see if we go p context slash decompressed dot data plus int of strlen of context slash decompress, not that one, decompress. Where did it let me do it one time? And so now we've got to this point here, but we are looking for another header. So if we look at what our bits has, we've got 2 into the current bit, and if we look at what the data is, and maybe look at, like, verify head, and if we say just look at what that is as a thing, do that. We have done 2, so whatever we'll be doing would be shifted by 2. So we're kind of looking at this 1 for the 1 bit, and that would set it to be last, which is most important. So I guess here we will get that context last. And what happens when it is a last? Like, I guess we still get a thing, because we need to kind of clear out this stuff. Like if we look at that, we still have this kind of data here before we get into the data that we want. So I guess we'll be doing that. So this was our B type, and so our B type I think is just nothing, right? Yeah, so now our B type is no compression. It's actually kind of lucky that I did the no compression. Yeah, so now we are going to do the no compression. So the first thing it does is clear the bytes. So currently it has so if I look at p context slash bits, currently we've got index 0. We don't actually need to clear the bytes, so it's actually just going to take in this these values here. This is kind of cool. So this is now doing the non-compressed blocks, which I didn't think would actually come up, but it's because I wasn't actually checking the adler code. So we'll get the len. So the len is 0, and the nlen was just the opposite of it. So nlen should be -1, but it's like one is completely set and one's completely not set. So that kind of means it's the one's complement. So our assertion will pass. Now we have a bunch of data that we need to do. So we should get bytes, and bytes should be 0, right? And so maybe bytes equals this one here. I think if bytes do something like that, so we don't actually read it, but we will get to this point here. I guess when we're setting deflate finish, yeah, so the deflate finish will, I've just done a thing. Right, so we should be in a finished state. Yeah, state finished. So we were the last, so we returned from this, and now we're in the Adler state. Perfect. So the assertion is failing currently, but I think that's because the order that we need to do it, just because that's the way things are. So I think I want to get this and do a break on zlib.h and 812, and if we continue that, right, so at this stage here we have our S1 and our S2, and they should be theoretically the same. So if we shift up that 16 and then add on S1, S2 times 65536, we should get that value there. And I think if we look at uint 32t, and this is a pointer. If we look at what our context slash bits data has in it, deflate.bits.data has in it. It's got 0 in it. I wasn't expecting that. No, just show me what it is. Right, so we have a size of 0. Have we consumed it all? No, because we got the Adler, so if we look at that, it's kind of good that we have consumed it all, I guess. And then if we look at the S2 stuff. So this is the right value, it's just reversed, quite simply reversed. And so how do we reverse that? There is a function, h, so we want it to be host to network, and I guess L, yeah, so L for along, which is a 32-bit thing rather than a 62-bit thing. So if we did that, we should get the right number. So I think I want to do something like that instead. And this, I think, needs upper inet. Gosh. Okay. So it can probably go in this one. Include arpa inet.h, and do that. And if we like, can we like run this, no, we haven't run it before, but if we run and go xxd minus r fail4.hex, and yep, do it again, continue from there, continue from there. So at this point here, the source is out of date, I think, but I think this will get the thing. Yeah, so we got our bytes, and then so now we're in H2 now. Perfect. And if we get that, we should get a value, this value here, and if we paste that, that's like completely different. But this value, I don't know, it didn't like die. That failed at an assertion, 288. So that's when we're calling next bytes, and so we should always clear bits before getting bytes. So maybe it's that. Am I kind of thinking that through fine? Because I wonder if it's at this point here. Well, that's just a zlib here. We're still in there. So I think in Adler we want to clear bits first. We didn't like that. That is because one of the places I did it, this one should be like that, and that should be fine. Right, so that does some things. What were some things that were like failing? There wasn't really anything that was failing. I was just trying to make sure that I got the Adler code right, which it does seem like it is doing it. We get the Adler. I wonder if instead of doing this, if it is not equal to that, we should probably do like a context state equals zlib error and return the false. Otherwise, we would do a context state equals zlib finished, in case we call it again, because if we call it again, it'll try and get Adler code again. But this way as we do that, we don't want that, but do want that. Cool. Should we try a test again? So this has all just been doing kind of the zlib stuff, which is kind of fun. So if we did something on that, but if we get something to there and do it again, yeah, that looks all good, and our thing's looking good. So what I'm wondering is, maybe stopping because I've been going for nearly 3 hours. Time flies when you're finishing off your zlib. Compression algorithm. I like it. There's bits I could probably tidy up, like this could be joined up, but I think I like it like this because it's very clear what it's doing compared to the spec, where my thing with the actual zlib source code is it does not seem like it does some other things that you're like, wait, what? And like, I don't know. I feel like reference implementation should purely be a reference. But it is what it is. Right, cool. So if that's that, I guess we can like submit this. So maybe I will get all this going. Git commit, git handler, and maybe we can get push that up. I don't know if that pushes to GitHub or somewhere. There's probably some commits I need to clear up. That point pushed it to that. So I think I need to git checkout master and then git merge test test into here, and it is just a fast forward. Perfect. And maybe we can go git branch minus d test and push to, I guess, git mine and delete that test branch. Not allowed a default branch of a project. Is it the default branch? Why on earth is master not the default branch? I would have to do something like that. It's too much effort there. But yeah, what I can do is now do submit and basically get to the next stage, which will help test the zlib implementation quite a lot, because I assume, now we have to create a blob, so we have to kind of do the inverse of doing that and like hash a blob, and it should make an object that would then do that. But yeah, that's for another day. Until now, thanks heaps for watching. I understand this one was a little longer, but hopefully it's exciting to other people that the zlib thing has kind of gone this far. I'll try and get it pushed up somewhere public in a more like tidy form. It might actually be up on GitHub by the looks. Like get remote must be. Yeah, we have like. So do I need to push origin and delete test branch there? I don't know. Yeah, we just have GitLab, which it doesn't really matter because it's private, I believe. Mine was what it was. But yeah, it's up on GitHub, but it has kind of auto commits like this auto backup and auto backup and auto backup and stuff, and it has stuff in the thing that you probably don't need, like a.temp, and it might even have like a 3 file. Gosh. So if I like rm3, that was just a file that was in thing. But yeah, had some C source code in it. That's all right. So yeah, I think I'll leave that there and clean that up at some point. But yeah, thanks for watching and hope you have a great day, and I'll see you another time.